So, last class I was solving one problem where foundation was subjected to both vertical and the horizontal load, and horizontal load was parallel to length. So, as per Henson bearing capacity theory, we have to do some modifications, and that I have done only the depth correction factors, and then we have to calculate the shape correction factors and the inclination corrector factors. So, that I will do in this class. So, here, so this is the problem that load, vertical load was acting with 1000 kilonewton, horizontal load was 300 kilonewton, and horizontal load was parallel to the length of the foundation, and it is parallel to B, the horizontal load is 0, but that can be both also. So, and then I talked about some how to convert the, if the phi value is measured in triaxial, and then you have to use it for under plane strain condition, and then we determine the, because as your HL is not equal to 0, then you have to go for two sets of factors and the equation. So, that I did for depth correction factors, that dQB and dQL. Okay. And now, d gamma B and d gamma L is 1 as per the Henson bearing capacity equation. So, now I will go for the inclination factor first, because that inclination factor you have to multiply with the shape factor. So, with certain term in the shape factor. So, now here I q b, which is equal to 1 minus 0.5 say h b divided by v a dash, because here a dash and a are same, and then C A cot phi. And remember that if there is a horizontal load and the it is inclined also, vertical load is inclined, then eccentric, then we have to use that B dash L dash as per the suggestions given by different theories. Even Henson also, as per the suggestions, you have to use B dash A dash. That means, for inclination factor and the shape factor, you have to use B dash L dash, and in the third term you have to use either B dash or L dash, and for depth factor you have to use L by L and B. Remember that. So, this is your value, and now this is equal to 1 as H B is equal to 0, because H B is equal to 0. So, this will be equal to 1. Similarly, that I gamma B, which is equal to 1 minus 0.7 H B divided by V plus A dash C A cot phi. So, and that is to the power 5 actually. As I mentioned, if nothing is mentioned in the question, I will use this value as a 5. Okay. But as I discussed in previous class, that some researchers have suggested to use the a lower value. Okay. But if it is mentioned and the range is given, if it is mentioned that you use this value, then only in the question or in the example problem I will use that. Otherwise, I will go with the original one, which is 5. So, this is equal to 5 as H B is equal to 0. And then now I Q L, okay, which is 1 minus 0.5 H L divided by V plus A C A cot phi, because A dash same. So, now as the C A part, that means the C is 0. So, this part will be 0. Okay. So, now the equation will be 1 minus 0.5 H L divided by V only, because C A part is C A is 0, equation is 0. So, that will be equal to 5. So, this is equal to 1 minus 0.5 H L is equal to 300 and V is equal to 1000, that to the power 5, that is equal to 0.444. Similarly, I gamma L, which is 1 minus 0.7 H L divided by V plus A dash C A cot phi to the power 5. Similar to here again, that your C equal to 0. So, I will neglect that. So, I will write 0.7 H L is 300 divided by 1000 to the power 5, this is 0.31. So, I have calculated these factors. So, now I will go to the modification in the shape factor. Okay. So, now I will calculate the SQB. SQB. So, this is 1 plus sin phi, and we have done the modification, that is B I Q B divided by L. Okay. And if loading is not inclined, then I Q will be 1. So, that will go back to our original table equation that I have given. So, but that type of modification is not required for others theory, it is only required for the Hansen theory. So, now this is equal to 1 plus sin phi is sin 40 degree, and B is 2, and IQB is equal to 1, because your IQB is equal to 1, I gamma B also equal to 1. So, that is 1, L is equal to 3. So, this is 1.43. Then SQL is equal to 1 plus sin phi, then L IQL divided by B. So, this is 1 plus sin 40 degree, L is 3 meter. Now, IQL is 0.444 divided by 2. Okay. So, IQL is 0.444. So, divided by 2. So, that value is also 1.43. Now, S gamma B is equal to 1 minus 0.4. Now, B I gamma B divided by L I gamma L. Okay. And that should be greater than equal to 0.6. So, now I can write 1 minus 0.4, B is 2, I gamma B is 1, then L is 3, I gamma L is 0.31, because this is 0.31, this is 0.31. So, this value is 0.14, as it is less than 0.6. So, use 0.6, because it should be greater than equal to 0.6. So, use 0.6. Then S gamma L. So, that is equal to 1 minus 0.4 L I gamma L divided by B I gamma B. That should be also greater than equal to 6. So, I can write 1 minus 0.4, L is 3, I gamma L is 0.31 divided by 2 into 1. So, that is equal to 0.81, which is greater than 0.6. So, use 0.81. Okay. So, now we have calculated two sets of factors, depth factor, shape factors and inclination factor. So, now I will use the two sets of equations. So, that is net ultimate bearing capacity. So, this equation will be C part, first part is 0, then gamma df, NQ, then SQB, DQB, IQB plus half gamma b n gamma S gamma b d gamma b I gamma b. Again all the cases I am mentioning that if there is a compressibility effect that you have to incorporate compressibility factor, but the data is not given, that is why we are not incorporating that. So, that is minus gamma df. So, now I put that this is gamma is 19, df is 1. Okay, so that depth of foundation is not given. So, that depth of foundation is df is equal to 1 meter. Okay, so, this depth of foundation is 1 meter. Okay, so, this is 1 and for phi equal to for phi equal to 40 degree, n q is 64.1 and n gamma is 79.5, that I will get from the table of Henson's bearing capacity equation 64.1 and 79.5. Okay, so, this is n q is 64.1, then s q b is 1.43, then d q b is how much? D q b is 1.107. So, this is 1.107, then I q b is equal to 1, then plus half into 19 into b is 2 meter into 79.5, then S gamma b is 0.6, sorry S gamma b is equal to 0.6. Okay. Then d gamma b is 1 and then I gamma b is also 1. Okay. And then minus 19 into 1. So, this value is coming out to be 2815 kilonewton per meter square. This is one set of equation. Now, we will go for the next set of equation, and that is we have to replace B by L. So, this will be gamma df n q s q l d q l I q l plus half gamma b n gamma, sorry, this will be gamma l. This will be gamma l, then S gamma l, d gamma l and I gamma l minus gamma df. So, I will put this value 19 into 1 into 64.1 into XQL, which is 1.43, then DQL. DQL is 1.071. So, DQL 1.071, then IQL is 0.444. Then plus half into 19, L is 3 meter into 79.5, d gamma L is 0.3 d gamma L, S gamma L is 0.81, then d gamma L is d gamma L is equal to 1 and I gamma L is 0.31. So, this is 1 into 0.31 minus 19 into 1. So, this is coming out to be 1378.1 kilonewton per meter square. So, the minimum of these two will give us the Q net ultimate or ultimate bearing capacity. So, Q net ultimate is equal to 1378.1 kilonewton per meter square. Now, you have to calculate the factor of safety. So, for the factor of safety for bearing, that is equal to that total load the footing can carry, that is 2 into 3 area into the net ultimate bearing capacity, that is 1378.1 divided the total load that is acting on the footing, and that value is 8, which is very high, okay, which is very high. But let us see factor of safety for sliding is equal to that your T, that is V tan delta plus A C A divided by H. Now, A C A is 0. So, that will be V is 1000, tan delta is taken 0.8 times of phi, and this is H. Okay. And one thing I want to mention, that sometimes it may happen in that your this is the foundation base and this is the ground surface. Now, soil this zone and soil this zone can be different also. So, now when you calculate that delta and the CA, do not take the soil of layer 1, soil properties of layer 1, you take the soil properties of the layer 2, because it is the base interaction. So, where the foundation is resting. Okay. So, this is the here the properties that you have to consider for delta and CA. Similarly, for again the second term, because there is bearing capacity 3 term, second term gamma will be this gamma 1, and the third term gamma will be gamma 2, because that is below the base of the foundation. So, remember that. So, now here it is 1000 into 10 0.8 into 40 degree, and the H is 300 degree 300 kilonewton. So, which is 2.1 greater than 1.5, it is fine. So, bearing capacity factor is very high, but as per the sliding it is more or less okay, but still you can reduce some bearing some factor of safety, because it is again you can reduce sometimes. So, you can modify your design, and then you can slightly make the design economical also. But here the only the bearing capacity are asked to, or the factor of safety are asked to determine. So, that is why we have determined the factor of safety. So, but here it is very high, but as per the sliding it is okay, but still you can modify the design, because it is over safe, you can say. So, this is the example to calculate the bearing capacity for inclined load as per the basic bearing capacity equation. And remember that suppose if your HL is equal to 0, but HB is not equal to 0, then these two sets are not required, only one set you have to do, that HB1 that DQB1, but this modification you have to do, this modification 1 plus sin phi B IQB, that modification you have to do, but only that L part no need to do, only the B part is sufficient, and only the equation, first equation you have to use, not the second equation. Okay. So, this is these two sets is only you have to go if HL is not equal to 0. Now, the next effect that I will discuss, that if the foundation is with tilted base, that means now till now we have discussed the foundation where the base is perfectly horizontal, but there may be a possibility that foundation base can be tilted also. Suppose you have a foundation like this. So, this is your foundation which is tilted. Okay. So, which angle of eta, okay. And then this is your say, because that can be like this also, this is your ground surface and here it is the ground surface can be in the same level. Okay. But your foundation is tilted, it is not our normal foundation is like this, where the tilt is 0. This is our foundation, where tilt is 0. But here the foundation is tilted with an angle. Then how we can determine the bearing capacity? And another option is that, or another case is that foundation may be in the sloping ground. Then how we can calculate these bearing capacities? That our foundation is in the sloping ground. For example, this is your foundation, this is a slope, okay, and your foundation is here on the top of a slope. It may be on the surface of the slope or it may be with a distance with a depth. So, this is your B. Okay. So, this is the slope with an angle of beta and this is the height of the slope. Clear? Now, how we can calculate the bearing capacity in such cases, that the foundation on top of a slope or foundation with tilted base. Now, it can be both also, that foundation on the slope plus it is tilted also. For example, like this, that this is the foundation is tilted one, okay, and then it is tilted foundation and it is on the slope also. So, that means it is on the slope also, okay, with an angle of beta say, but it is at the same time it is tilted. So, that different combinations can be possible, that it has both eta and beta. So, this case your beta is not equal to 0, okay, but your eta is equal to 0. This case eta is not equal to 0, but beta is 0. This case eta is not equal to 0, beta is also not equal to 0. So, that means foundation is on the slope, at the same time it is tilted. So, then how we can calculate the bearing capacity, all those things that we have to discuss. So, now if the foundation is on the slope and foundation is a tilted base, this tilted base, then the Vesic and Henson has suggested the factors. Now, as I mentioned that originally we know that there are 3 correction factors, that is shape factor, depth factor, inclination factor, but I have discussed about one more factor, that is the compressibility factor. Now, here 2 more factors are introduced by Vesic and Henson, that is the G and the B. G is the ground factor, that means base on slope, if the foundation is on slope, that is the ground factor, and B is the base factor if it is a tilted base. So, that means the SC, DC, IC, GC, BC. Okay. So, that means this is G is the ground factor if foundation is on the slope, and B is the base factor if it is a tilted base. Okay. So, these two factors are also introduced. In addition to that, if we have the properties, then we can introduce the CC also. That means, there are 6 total factors: shape factors, depth factor, inclination factor, ground factor, base factor, and the compressibility factor. So, these 6 factors can be used. So, this base factor and shape factor is, these two factors are proposed by Henson and basics bearing capacity theories. So, these two theories. So, now what is the G, how I can get the ground factor and the base factor? So, this is the GC expression, beta is the slope angle, and this is 147, these are all degree if phi equal to 0, and GC is equal to can be determined by using these equation if phi is greater than equal to 0, and GQ and G gamma can be determined by using these equation for any phi value. Similarly, BC also can be determined by using this equation for phi equal to 0, and BC by this equation if phi greater than 0, and BQ by this equation. But remember that here eta is in radian, and B gamma also can be using by using this equation, can be determined by using this equation, where eta is also in radian. Similarly, for as per the basic, this is the table by which we can determine the ground factors and the base factors, and remember that all these beta and eta are in radians in these equations. That means, actually it is in degree. So, when you put them in this equation, you have to convert them to radian, okay, by which we can determine all these factors as suggested by Henson and the basic. And then one thing that I want to mention, that here Meharov also suggested that how we can determine the bearing capacity when foundation is resting on a slope, and Meharov suggestion. So, this is the normal, these two are the suggestion by the Henson and the basic, where it is in the slope and the place is tilted. Meharov is also suggested, and he has incorporated the effect of this footing distance or edge of the footing distance from the slope edge. Okay. So, that is called small beta, but that effect, that the distance of edge of the foundation from the slope edge is not in this in the factors, those are suggested by Henson and the basic, where this b value effect is not, small b value effect is not there, because whether you place the foundation at any distance, you will get the more or less same factors, because those factors are function of either beta or function of eta. You can see these are all either function of beta or eta. Okay. So, that depth is not given, but Meharov has suggested when foundation is resting on a slope with the distance of the foundation edge from the slope edge. So, but Meharov has not given again this tilted base factors. Okay. So, that means, if you go for tilted base case, then you have to go only for basic either or Henson. But if you want to go for slope, if foundation is on the slope, then you can use either basic or Henson or Meharov. Okay. So, in the next class I will discuss that or I will solve one particular problem, and then I will discuss all these effects, that how you can determine the bearing capacity when its foundation is resting on a slope by using Meyer approach, then Henson's and basic approach, and if the foundation has a tilted base, then how you can determine the bearing capacity by using Meyer and the basic approach. So, these things I will discuss in next class. Thank you.